you'll need to take some notes here. I hope from our opening door thing, remember the opening door thing that we did over there? So you're starting to get the idea of going from average rate of change when the two dots are separated to instantaneous rate of change, just sliding one dot right over on top of the other. Okay? Yep. So in terms of geometry, the average rate of change is the slope of the secant line. We're doing that in pre-calculus right now. I'm handing them a function, a curve, not a line. Because then the average rate of change is just m if I hand them a line, right? It's just the slope. But if I hand them a curve, the average rate of change, the geometric definition is the slope of the secant line. The algebraic definition is simply f of b minus f of a over b minus a, also known as y2 minus y1 over x2 minus x1. So in pre-calculus, what we're doing is calculating average rate of change. They don't know where this is headed yet. They're a ways off from that. But average rate of change is just finding, and I'll draw a picture down here of the slope of the secant line. And I've done it with functions, and I've done it with pictures. If I don't give them a function, they have to know the two coordinates that connect the two endpoints, and then just find the slope using y2 minus y1 over x2 minus x1. The instantaneous rate of change, I'll draw pictures. Instantaneous rate of change is the slope of the tangent line, which is what you're seeing in that geometry sketchpad opening door activity. As they were having you slide that point closer and closer, you were approaching the slope of the tangent line, right? So eventually one dot is on top of the other, and then you have exactly the slope of the tangent line, which is the derivative we're going to learn next.
That's what I think right now, yes.
So what I'd like you to do, don't write, just draw a graph, an XY graph with only the first quadrant, like I have here. And then we're going to draw just the right half of the curve y equals x squared. So at 0, 0, put a dot. At 1, 1, put a dot. 2, 4, 3, 9, and we'll stop right there. And then we're going to draw a picture of a secant line to this right-hand side of the curve y equals x squared from the origin to x equals 2. So the secant line will go from 0, 0 to x equals 2. From your geometry days. What makes that a secant line? Remember the definition of a secant line? Yeah, it's kind of inside of the arc. We usually define these in geometry in the context of circles. Yeah, it's just 2 points in the curve, as opposed to a tangent line, which touches only 1 point. So we'll draw a tangent line at x equals 2 next. Okay, so draw your tangent line at x equals 2. It touches at only 1 point, at 2, 4. Would you agree that these two have different slopes? Yes. One of them represents the average rate of change over an interval, and the other one is the instantaneous rate of change at a particular point. So you can figure out what they're talking about in context. Average rate of change has to be over an interval, from x1 to x2, or from A to B. Whereas instantaneous rate of change, they're going to ask you for a specific point. So they might say, what is the instantaneous rate of change of my rocket, at x equals, see, I think the longest that one was in the air was like almost 4 seconds. So at x equals 2 seconds. And we're asking for the exact speed. Really isn't that high, huh? Yeah.
4 seconds.
And one of those only up for 4 seconds. There may be some that were they're equivalent to about a punted football or something. Yeah. Doesn't seem like the air pump is holding it up. The bigger pressure gauge is at home. So, you guys see the difference between average and instantaneous rate of change geometrically? Okay, and then algebraically, to do instantaneous rate of change, we're going to need to add in limits. But algebraically, average rate of change, here it is. It's just your old slope formula from Algebra 1. Yeah.
I'm sorry, why are there 3 lines?
3 lines. Well, there's the curve,
Oh,
and then the secant line and the tangent lines.
oh, okay.
Yeah.
So what you're saying, let's average.
All right. So here's an example. If f of t equals 16t squared, find the average rate of change on 0, 2. So we know our average rate of change equation, when we're given a function, is f of b minus f of a over b minus a. Well, in this case, a is 0 and b is 2. So I have f of 2 minus f of 0 over 2 minus 0. And f of 2 is going to be calculated by plugging in 2 for t. So I have 16 times 2 squared minus 16 times 0 squared over 2 minus 0. So my average rate of change from 0 to 2 seconds, if you will, would be what? 16 times 4, 64 over 2 is 32, and whatever the units are. I have something like feet per second. Average rate of change, we can do that with algebra. Okay? Slope of the secant line, we can find it out. Here's our problem. I need 2 points to get the slope of a line. And when I have a tangent line, I only have 1 point. So what we need to do is be able to slide the point as close as we want to it. Does that sound like a limit? We're sliding a point as close as we want to a particular point is a limit. So our definition here, and here's why you learned the difference quotient last year. But the slope of a curve, f of x at a point, this is called the slope of the tangent line. You might state that here in a minute. But the slope of a curve, f of x at a point, p, a comma f of a, is the number m equals the limit as h approaches 0 of f of a plus h minus f of a over h. And that is exactly the difference quotient you learned last year. But now we're applying a limit to it. So what we're saying is the limit as h approaches 0. So here's my picture. Parabola again. So if this was, say, x right here, and this is the point x plus h. And what we want to do is look at the limit as h approaches 0. You see how that is equivalent to sliding the point at x plus h over towards the point x? If h is 0, then I'm, or is it approaching 0, I should say. It's a limit. But if h is approaching 0, then that means I'm sliding this point as close as I possibly can to x. So we are going to define the instantaneous rate of change as this, right here. There it is. Another phrase for the instantaneous rate of change, geometrically speaking, is the slope of the tangent line to a curve. Okay? We're going to go ahead now and find the instantaneous rate of change, or the slope of the tangent line now, using this definition. And then I should do that in your homework as well. So here we go. It says find the instantaneous rate of change at, you see the difference here between this and the average? It says at x equals 2. Whereas the average one, what did you notice? on an interval. Okay, so it's a big difference. So it's m equals the limit as h approaches 0, okay, of f of a plus h. So this is telling me to take a plus h and plug it in place of t. So f of a plus h would be 16 times a plus h squared minus f of a would be a squared, yeah, all over h. Unfortunately, you're only going to have to do this a few more times, and then we'll leave this behind, and I'll give you some shortcuts called it's the derivative, okay? So bear with me here. But you need to understand this limit definition of the derivative. That's what this is, really. This is the definition of the derivative. And then we'll learn some shortcuts. So here we go. A little bit of algebra to do. You got a lot of this. Lots of different functions. So limit as h approaches 0. A plus h squared is going to be a squared plus 2ah plus h squared. Just expanding out that binomial. Minus 16a squared all over h. And I'll go ahead and distribute here. Limit as h approaches 0 of 16a squared plus 32ah plus 16h squared minus 16a squared all over h. You remember this last year?
Yeah.
So things will cancel. And h will cancel, right? So this h will cancel with this h here. And then one of the h's here will cancel with this h down here as well. So I have the limit as h approaches 0 of 32a plus 16h. And then go ahead and evaluate this limit as h approaches 0. We just plug in 0 for h. So that's gone. It's 32a plus 16 times 0. And that equals 32a. Now, that's actually an expression for instantaneous rate for f of t equals 16t squared. So what we just found is a generic expression. So you plug in any value of a you want. In this case, I wanted a equal to 2, right? So if you evaluate, find 32 times 2, and you get 64 as your instantaneous rate of change. Instantaneous at x equals 2. So there are a couple different ways you could approach this. I don't have you do both in the book. I did it in such a way it's kind of a generic instantaneous rate of change that will work for any function. But if you want a particular value of a, what you could have done is replace a with 2 up here. So see up here at the beginning, I could have just put in a 2 here and a 2 here. And just put in a 2 right here and a 2 right here, and then at the end, you would have had your instantaneous rate of change of 64. In the homework, they're going to ask you to do both. They're going to say, find the instantaneous rate of change for x equals a. So you'll have another, you're really just coming up with another function. By the way, it doesn't matter if this is a or x or whatever. What kind of function is this? If I call this, oh, g of a equals 32a?
It's a linear.
It's a linear function. Okay. And what did I start with?
A curve.
A curve, a quadratic. That's second degree. And this one is first degree. Okay. It's no accident. So, geometric definition of the difference quotient on geometry sketchpad. I think you kind of already saw this. I'll show it to you again here. But we drew a picture of it here today as well. Give you a picture one more time. Okay, so I think I can grab this, slide it. Here's what you were doing the other day. But there's average rate of change. Okay, you could find the slope. I think I have a slope up here. There it is, 0.345. But as I slide this closer, so it's right on top of it, up, there's our instantaneous rate of change. And there's the slope here. And I put the difference quotient up here. This is f of, it's hard to see, f of a plus h minus f of a over h. But now we have those 2 points. Now they're together. Remember how to separate them out. So there's my tangent line. What you can see here is the tangent line. There's an instantaneous rate of change of about, can I get 0? I don't know if the fine motor skills to do that. So there's one of about 0. That's an instantaneous rate of change of about 0. What's going to happen when I go this way? It's negative. Instantaneous rate of change is negative, yeah. Over here, very fast. It's, well, I don't know about very fast, but faster. It's 1.236. That's not really that fast, but it's over 1. So, all right. Any questions on this? So, you're going to be asked to calculate average rate of change. So we're going to find what's called the normal line to a curve. This really amounts to just finding the instantaneous rate of change and then taking the, well, here's the definition of a normal line. The normal line to a curve is the line perpendicular to the tangent at that point. So if it's perpendicular to the tangent at that point, how will its slope be related? Yeah, negative reciprocal, that's right. So it says find the equation of the tangent line and normal lines at x equals 3 for the function y equals 1 over x minus 2. So this function has a vertical asymptote at x equals 2. It's got 2 branches, one here and one here. And what I'm trying to do is find the equation of the tangent line to this curve at x equals 3. I'm trying to find the equation of that red line at x equals 3, and also the normal line at x equals 3, which would be that one. So we're going to find the equation of this line and this one. Give you a couple minutes to draw that picture and to understand what we're being asked to do. Let's go ahead and find the equation of the 2 lines. Our answers will be 2 separate equations. What's helpful, I think, here is just to, as a review, write down point slope form of a line. And we're gonna leave it in this form, and I'll show you how to change it to graphing form without ever actually putting it in slope intercept form. So that's point slope form of a line. If you don't remember that, I would write it down. You can use this a lot. So we're going to get the equation of our lines in that form. And we need to know 3 things. We need y sub 1, m, and x sub 1. I'm given x sub 1 right here. Right? X sub 1 is 3. That's the x coordinate of the point of tangency. So I know my equation is going to be y minus something equals m x minus 3. Now, how do I get y sub 1 with what I'm given here? Plug in something, yeah. I mean, y sub 1 is just asking for the y coordinate that goes with 3, yeah. So you're just plugging in x equals 3 to equation given. So it looks like this. Y minus, we can do it over here. Y equals 1 over 3 minus 2. Y equals 1 over 1, which is 1. So y sub 1 is 1 equals m x minus 3. I'm almost there. I have to do some messy algebra here now. How am I going to get the slope m for this equation of the tangent line? Yeah. Use difference quotient, right? So we use a difference quotient to get m. And the difference quotient says, we'll do that over here, m equals the limit as h approaches 0 of f of a plus h minus f of a over h. What is a in this case? Try to plug a directly in. 3. So it's asking for limit as h approaches 0 of f of 3 plus h minus f of 3 over h. And I think it'll be helpful to go ahead and plug 3 in for h in this case. The reason for that is we already know what f of 3 is. We just evaluated it. Right? F of 3 was equal to 1 that we did to get y sub 1. F of 3 plus h is telling me, if you look up here, there it is, to plug in 3 plus h for x in this function. Okay, this is a hassle with rational functions. It's a bummer. But we have 1 over 3 plus h minus 2. Minus f of 3 was 1 all over h, and we have a algebraic mess. We can do it. This will be the hardest part of this lesson, is just doing the algebra with rational functions. You'll be really glad to see that there is a shortcut on this. It's coming soon. All right. So here we go. Limit as h approaches 0. This is 3 minus 2 is 1, so this is 1 over 1 plus h minus 1 all over h. I left space here for a reason. This is a complex fraction, right? No. I'm plugging 3 plus h in for x in this function. And then I'm also plugging 3 into this function to get the second part of it. When I simplify the bottom, I get 1 plus h. What do I have to do to join these two fractions together? Common denominator. So I got to multiply this by this thing. Doesn't have to be multiplied by anything, right? But I have to multiply the 1 by 1 plus h over 1 plus h. So I have limit as h approaches 0. The top of this is going to be 1 minus h, right? All over 1 plus h all over h. And everything's going to turn out all right here. 1 minus 1 is 0. I have negative h on the top over 1 plus h. And how can I turn this division into multiplication? Flip it. Flip what? The bottom. What is the bottom?
H over 1.
H over 1, okay. So baby steps here, yeah. This is h, or h over 1, so it's going to become times 1 over h. And this, every rational function will have the same type of thing happening, okay? This is the first time we've seen the algebra with a rational function. The h's cancel, leaving me with the limit as h approaches 0 of -1 over 1 plus h. Can I evaluate that limit by substitution? Yeah. Plug in 0 here, what do you get? 1. Yeah, and 1 plus 0 is 1, and then -1 over 1 is -1. Yeah, so this becomes -1. So all that to find the slope. You don't have to show all your steps though, but you need to be able to do the algebra to find the instantaneous rate of change or the slope of the tangent line. Yeah.
Why again? I'm like step.
-1. All right, so my equation of the tangent line. We're ready for it now. Tangent line equation is y minus 1 equals -1 x minus 3. That's the tangent line equation. Since you haven't probably memorized the normal line equation. The relationship between the slope of the tangent line and the slope of the normal line is that they are opposite reciprocals. You'll have to memorize that. So the normal line equation is y minus 1 equals +1 x minus 3. Okay, all I do, I keep the point the same. Look at my picture up here. The tangent line is this one right here. The normal line is this one right here. So they both go through the same point, but they have opposite reciprocal slopes. So the equation of my tangent line is this. Y minus 1 equals -1 x minus 3, and my normal line is the one below it. All that changes is the slope. And if I change that to slope-intercept form, just make sure that this makes sense. Look up here. It should be this one right here. That's the tangent line. It looks like it has a negative slope, and it's going to go through a positive y-intercept. Well, take this. Distribute the -1. You'd have y minus 1 equals -x plus 3. And then add the 1 over y equals -x plus 4. Does this line right here look like, well, it's not very accurate. Does it look like it has a slope of about -1? And a y-intercept that's positive at least, right? Somewhere around 4. So my sketch was very rough. But it should be going through a y-intercept of 4. And this other one down here has a positive slope and should be going through some y-intercept down below the x-axis. What they'll do on the AP exam is they will oftentimes just write this as y equals -1 x minus 3 plus 1. That's in the scoring guidelines. All they'll do is take this and add it over, and then it's in graphing form. They don't actually put it in slope-intercept form. And you don't have to. The only reason you would put it in slope-intercept form, or even this form, is if you were asked to graph it on your graphing calculator. And I think there are a couple problems they ask you to do that. And that's a good idea because this equation, if you've done all your algebra and arithmetic correctly, these should actually look like the equations of the lines in your picture. So I'm going to ask you to draw the picture like I did here and make sure they at least look like they're going through the correct y-intercept and have the correct slope. Okay. This is bread and butter of the AP. This is asked on the AP exam. Okay. It's something you'll be asked to apply probably on the free response and the multiple choice. You'll have a tool called the derivative that you can use to do it without all the algebra. What's that? Where we started. You remember what the question was? We started with this function, y equals 1 over x minus 2, and we wanted to find the equation of the normal and tangent line at the point x equals 3. To change the problem up, all I have to do is change this to another number, and then it's completely different equations, right? Because this is the equation of the tangent line at x equals 3 only. So that was the question. You're going to ask to do that on the homework. All right. Let's do one more example here. One more, why not? And then I'll have you try maybe 2 problems from the homework assignment. 2 or 3, so we have time for. It says find the slope of the curve at x equals a and describe what happens to the tangent at x equals a as a changes for the function y equals 2x squared plus 3x. So find the slope of the curve at x equals a. What does that tell me I'm doing? Instantaneous rate of change, yeah. Which is primarily what you're going to be doing in this assignment. They have some average rate of change, but we're leaving that behind. Instantaneous rate of change. And describe what happens to the tangent at x equals a as a changes for the function y equals 2x squared plus 3x. So we're doing this in a generic sense. We're going to get an equation. By the way, what will the degree of my equation be? Somebody knows.
2.
That's a good guess. Why do you say 1? 1 is correct. Yeah, we learned that, yeah, these polynomial functions, when we get the instantaneous rate of change, or what we'll discover is the derivative, it goes down like that. Yeah. So we're going to get a linear function that represents the slope of the tangent line at a. And then we're going to evaluate, just think about what happens when a is negative, when a is 0, when a is positive. Okay. So what do I do to start this problem? Finding, well, no, we don't need that on this one. We're finding instantaneous rate of change. That equation, yeah. M equals limit as h approaches 0 of f of, now I don't have a specific number to put in, so it's just f of a plus h minus f of a over h. So limit as h approaches 0. Here we go. What is f of a plus h going to be? We'll put that in this bracket, and then what is f of a going to be? We'll put that in that bracket over h. So first of all, what is f of a plus h going to be for this function? 2, yeah, a plus h squared plus 3a plus h. I'm replacing x in both places with a plus h. And then minus 2a squared plus 3a. I'm replacing x with a plus h for the first term and replacing x with a for the second term. You could probably have just left it in x if you wanted to. X, it doesn't matter. All right, so limit as h approaches 0. Okay, this should be no problem here. Let's expand this out and multiply by 2 at the same time. You ready?
Okay.
What are the terms? What's the first term? 2a squared plus, okay, 2ah in the middle, and then times 2 is going to make it 4ah plus 2h squared, and then plus 3a plus 3h, distributing that, minus 2a squared minus 3a all over h. Okay, what do we expect to happen next? Some canceling. What cancels? 3a's are gone. 2a squareds are gone. And 1h from each of the terms left on the top will disappear. We'll cancel with the, so we have limit, same thing will happen each time. So, you know, you don't need to get caught up in the algebra here. It's okay. We have 4a plus 2h plus 3. Did I get it right there? Over 1. So we don't need to even write that. So there it is. And then my final step is plug in 0. So this equals 4a plus 2 times 0 plus 3 which is 4a plus 3. So what I'm saying is that m equals that, and actually m is a function. It's a linear function, right? 4a plus 3. So on these types of problems, I like you to consider a for a less than 0. What can you tell me about m? Well, I don't even know. Maybe that's not how you want to do this. Let's graph it. What's the x-intercept or a-intercept in this case? When does this thing equal 0? 0 equals 4a plus 3. We might want to break this up a different way. So a equals negative 3/4, right? So that line passes through an x-intercept of negative 3/4, 0. So 1, 2, 3 up, slope of 1, 2, 3, 4 down, 1 over, so negative. Should be a little bit more. 1, 2, 3, 4 down, 1 over, so right here. So it's passing through like that. Does that look like a y-intercept of about negative, or x-intercept of about negative 3/4? So that's what it looks like. So what can you tell me? Let's break this into 3 pieces, right? M is negative for what values of A? When A is less than negative 3/4, right? And M is 0 when A equals negative 3/4. And M is positive when A is greater than negative 3/4. So what we have here is, now this is very different. I know we're talking about M, and you want to say M is 4. But M is not 4 in this case. We're talking about M being the slope of the tangent lines to the curve of the quadratic. So what this is showing me here is if I were to graph this quadratic up here, the original quadratic, 2x squared plus 3x, we should graph it actually. 2x squared plus 3x, when A is negative 3/4, it has a slope of 0. What does that tell me about the quadratic function? Can you tell me the min or max of the quadratic function? Yeah, what is it? What's the x value of the min? Yes, at negative 3/4, you have a vertex. It's leveled out. And to the right of negative 3/4, is it going up or is it going down? It's going up. And to the left of it, it's up. I should say going up. I should say the slope. The slope is positive to the right of negative 3/4, and it's negative to the left of negative 3/4. Let's see.